Welcome. So, as promised, I will be doing projectile motion problems and putting those formulas that we've been deriving since part 1 and part 2 into use. So, the problem we'll be doing today goes as follows. So, a friend tosses a baseball out of his second floor window with an initial velocity of 4.3 meters per second, 42 degrees below the horizontal, and the ball starts from a height of 3.9 meters, and you catch the ball 1.4 meters above the ground. So the tasks are: calculate the time the ball is in the air, determine your horizontal distance from the window, and calculate the speed of the ball as you catch it. So, to get an understanding of the situation, we must have a full picture of the situation. So I've drawn it out for you. So here it is. Okay, so there are two people here. It's you and your friend. Your friend is 3.9 meters above the ground, and he throws a ball and then a baseball, and you catch it 1.4 meters at 1.4 meters. So that's it. You catch the ball. Okay, so in any projectile motion problem, always um know your initial velocity. So your initial velocity. So what does the problem tell us about its initial velocity? So we go back. So as you can see, it tells us that it is 4.3 meters per second and 42 degrees below the horizontal. So that's that. So that's 4.3 meter per second and 42 degrees below the horizontal. That takes time to write, but you know what's better? Um, just use a sign for it. Okay, so since it says that it's below the horizontal, we use negative, because had it been above the horizontal, it would have been positive. So that's that. All right, so we now break it down to its components, since, as we remember, velocity is a vector. It has an x and y component. So first, let us have its x component. So that is given by v naught times cosine of the angle. Okay, so what is v naught? Well, that's the initial velocity, the magnitude of it, which is 4.3. As a disclaimer, I will be omitting units to save time in writing. Now, multiply that by the cosine of the angle, which is negative 42 degrees. And pull up our calculator. That should be cosine. So it gives us there 3.195. So, excuse me, that is to be rounded to 3.2 meters per second. Alright, so we're done with the x component. Let us get to the y component. So the y component is given by the initial velocity multiplied by the sine of the angle. So what is the initial velocity? That's 4.3, and multiplied by the sine of the angle, which is still negative 42 degrees. Alright, so um, multiply that by the sign, you get negative 2.877, and round that to the nearest tenths, you should get negative 2.9 meters per second. Alright, so we're done with the components. Now, there's nothing really left here. Um, Let us now get straight to our tasks. So first, we calculate for the time the ball was in the air. Hmm. Actually, let's just use our theories first. How about we just list it, list them all out? So, in two different directions, x and y, we build a table of our formulas. So, in the rows, we'll have a for acceleration. So, the acceleration in the x direction is always 0. And in the y direction, that's negative 9.8. I'm I'm just leaving out the units. And next, the acceleration will be velocity. As discussed in part 1, the velocity in the x direction is just v naught x, or the x component of the initial velocity. In the y direction, velocity is given by v sub y, and then the y component of the initial velocity minus 9.8 times t, which is time. And finally, we got the position. So in the position of x, it is given by rx, and then the uh, initial x position plus v naught x times time. And in the y direction, that is given by r sub y, and then r sub y naught plus v sub y t minus this, we divide this by 2, so that's negative 4.9 t square. Alright, so that's that. However, for this, we just cancel this out. We just consider the initial position in the x direction to be 0, because as you can see in this diagram, we can just ignore the x. But for the y, we can't, since it starts at 3.9 meters above the ground. Okay, so those are our formulas. Now, we are ready. So, for letter A, we are tasked to calculate the time the ball was in the air. So, um, what what does this mean? So, since you caught the ball at 1.4 meters, so the ball was only in the air until you caught it 1.4 meters above the ground. So, when the ball was so when the ball so in other words, when y was no 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 when r sub y was 1.4 meters, you caught it. So we are looking at y of t equals 1.4. Um, this one, by the way, is also y of t. It gives the position of the object in the y direction as a function of time. So that's that. So, and the initial position in the y is 3.9 meters, since the ball was 3.9 meters above when the motion uh, transpired. Okay, so plugging in those to our formula, since we're looking for the time, we just get 1.4 equals 3.9 plus, well, initial velocity in the y, initial velocity, the y component of the initial velocity. That's what? That's negative 2.9. So that should be negative 2.9 t minus 4.9 t squared. So it is a quadratic equation, but we can use a calculator to solve for its roots. So let the calculator do the job for us. Oh no. And that's 3.9 minus 2.9. Let x be the variable, minus 4.9 x squared. Okay, so we get two roots. We get negative 1.069, and the other one, which is positive 1, 0.4077. Um, Negative for time is absurd, so we'll take the positive version. So we get t equals 0.48 seconds. So that's it for A. Now, for B, determine the horizontal distance from the window. So, it also occurs on the time when you caught it. Determine your horizontal distance from the window. So, what does horizontal distance mean? Horizontal distance means the x position. So, in our formulas, we will be using this one. So let us have that. So for B, we get Rx equals V naught x t. And since we're looking for R sub x, we get this. What is the x component of the initial velocity? So we calculated that to be 3.2. And what's the time? So we just calculated that. That's 0.48. And what does that give? So that is, so pulling up our calculator, that gives us what, 3.2 times 0.48, that's 1.536. So we just use 1.5 for that. So 1.5 meters. Okay, so we're done with it. Now let's do the final part, which is the speed of the ball as you catch it. So speed is in, oh no no, it means in this context that the speed is two dimensional. So we must have our x and y component. So we list the x component first. Component. So what's that? So the x component, in the speed sense, is always the the x component of the initial velocity. So that's always v naught x, which is 3.2 meter per second. But what about the y component? So since we are looking for the velocity in the y component here, in our table of formulas, this is the one that we should use. V sub y equals y component of the initial velocity minus 9.8 t, for which t is when you caught the ball. So plugging those in, v sub y, and then um, what is the y component of the initial velocity? So that's negative 2.9 minus 9.8 times the time when you caught the ball, which is 0.48. So carrying through the calculations, we should get negative what? 2.9 minus 9.8 minus 9.8 times 0.48. So that's negative 7.6. So we get negative 7.6. So we get negative 7.6 meters per second. So that's it for the x and y components. But we are looking for the speed. So we are just gonna use the Pythagorean identity for the magnitude of this vector. So for the speed, we get, or the magnitude of this velocity, that is given by this formula. So carrying this calculation out, that's 3.2 square plus negative 7.6 square. So all in all, we get 3.2 square plus negative 7.6 square. Okay, so we get 8.2. 8.2 meters per second. So that's it. We have solved our problem. So yeah, pretty cool, isn't it? Um, so to I will be uploading more videos of this, and yeah, we will be putting our formulas into more tests. So I hope you enjoyed watching, and take care, everyone. This has been Euler Phil.